Let's continue the discussion on graphic model semantics topology. And today we're going to talk about the representations for undirected graphic models. Just to recap, we have two types of graphic models. One are graphs with edges and directionalities. The others are not having directed edges. And what those edges and those nodes represents? Well, last time I think we covered one key concept, which is that those graph topology is telling you something about the conditional independencies between arbitrary subsets of random variables, three subsets of random variables. Usually they are expressed in the form of x independent of y, or independent of z given y. These are three subsets, could be singleton, could be any subsets. And we introduced a concept called deseparation in here, which can be graphically depicted, right? If you remember, verbally the deseparation is defined as a separation of phenomena in the graph where the two nodes are separated graphically in something called a moralized ancestral graph. Okay? And I'm not going to walk back to the very definition of that. And any three subsets of nodes satisfying the deseparation graphical criteria can be declared to be conditionally independent, okay, in also the distributions defined on the graph according to factorization law. And we went through a few other concepts such as a IMAP. IMAP means that a graph that defines a set of conditional independencies which all belongs to the honored independencies in a distribution. And also, by definition, you should be able to recognize that there is always a graph that can be called a IMAP of any distribution, which is the complete graph, because once the graph is completely connected, there are no independencies in the graph. Therefore, it is a IMAP of any distribution, right? And also, there is another more subtle and important definition called minimum IMAP, meaning that it is a graph. If you remove one more edge, you are going to introduce a new independence which is not present in the distribution. Therefore, you cannot remove any more edges from there to make it a IMAP, and that's called a minimum IMAP. And there are other additional ideas about I equivalence and all that, which I'm not going to use the time here to cover. I look at some of the discussions on the Piazza, and I feel maybe one question got a lot of attention, which is how to discover deseparation, right? This definition of moralized ancestral graph is kind of mysterious. It's a little bit unnatural. Yes, it is. It is for the sake of being tight and rigorous. But when you actually want to discover conditional independencies, you may not want to literally use the deseparation idea. Okay, you need to turn the graph, into an ancestral graph, then moralize it, and so on and so forth for every three subsets. Yeah, it's very, very cumbersome. So there are algorithms, okay, to make it easy. I actually skipped that from the last class, but I'm going to state this algorithm now. And I'm not going to prove it or further explain, and you can go home and review it. It's an algorithm that is known as a baseball algorithm, kind of a cool algorithm. Basically, it tells you a mechanical protocol, okay, to detect all the conditional independencies, okay, and also they entails deseparation as well in the direct graph. So there are three rules in the deseparation, in the baseball algorithm. One is this one. Basically, imagine that you have a graph which is hanging like this vertically, and you pass a ball from the source set X, and let them to basically traverse, maybe on gravity or in any natural course, through the graph to the other side. You want to ask whether my ball can reach to the other set Z. Okay, and there is a y in the middle somewhere. So here is the rule. If the y is in the middle or in the middle of the path, or right in the middle between the two sets of interest, you will basically follow the following. If y is observed, then your ball will bounce right back from y. Therefore, you cannot pass that. If the y is not observed like this, you pass it as if it doesn't exist. Okay, that's one law. And the second rule is if y is a common ancestor of the two nodes, then again, if it is observed, it's shaded, you bounce back, otherwise you pass. And then there is this third condition, which is a little bit trickier. That's actually, you can imagine, it corresponds to our this V structure. If the ball is shaded, is observed, you actually pass it. If it is not, you bounce back. Okay, so these are the very, very local rules that you need to follow. And you just follow it whenever you run into a node in the middle. Okay, and then at the end of the day, if your ball from here, just manage to traverse the graph and get to the other side, then they are not conditionally independent. And if you cannot get there, they are conditionally independent. Okay, why that happens? Well, you go home and hopefully convince yourself. Basically, you need to use this three minimum structure to prove all the deseparation properties. You can prove it formally. Remember that in the beginning of last lecture, we proved one thing, which is that if you are having this structure and you write down the joint based on the factorization rule, you can prove that they satisfy conditional independencies in the form of A independent of B given C. Right? You can actually prove that algebraically. Same thing. You can prove all the other properties algebraically just by using the minimum structure, which is a V structure and a chain structure, and also the common parent structure. And all these rules can propagate. Whenever you run into a node, you always run into these three basic structure, nothing more than that. And then you can establish a global set of such things. Okay? Yeah?
Like in that top left example, if the ball is sitting at node y.
No, it doesn't sit.
Well, I guess, like in that example, it's trying to get to x and z. That's cool. But I'm just saying in another example, if the ball was at y, can you assume that its neighbors?
You already observed it. What do you claim? You don't make any claim for something observed already, right? You're only conditioning on something observed, right? Okay. All right. I want to move on because there are a lot of good stuff in this lecture. But if you have any more questions, you can come to my office hour, okay, which is right after the class on Monday, or the TA's office hour, or we can do it in recitation. Okay. Then the IMAP concept naturally leads to something a little bit more profound and difficult called the perfect map, meaning that these two sets are equivalent. Okay. Do you guess that for any graph and any distribution, you can always expect a perfect map or a equivalence? Maybe the other question we'll ask is that can I basically imagine that for any graph you draw, there is it can be a perfect map of some graphic models, some direct graphic models. The theorem says it is not. Okay, so again, I can give you an example. That's a very, very famous and a very, very instructive. So a graph will really correspond to a conditional independent set, right? So I can basically write down these two sets. And it basically says that you have four random variables, A, B, C, D, and I want to have a conditional probabilistic distribution that satisfy these two conditional independencies. Now, you can draw, I give you a constraint that you can only draw this in the form of a direct graph model. How can you draw it? There are not infinite ways of drawing graphs over four nodes, right, in the direct fashion. Maybe let's try this. These are two graphs which are DAGs. And now you can tell me, do they honor these two sets of, let's call this AI, for example. Okay, and I have a P, okay, which honors only these two sets of I's. I can actually create such a P, such a distribution. Okay, now I ask you, do you have a perfect map in the form of a DAG? These are two maps. Are they perfect? Are they equivalent to this I set of P? Yeah.
B and 2. B and 2, the second one.
Uh-huh.
So that looks like it's equivalent.
Really? Okay. I believe in B2 you have other conditional independencies. For example, how about this is honored, right? It is a V structure. When you don't see A, these two are independent. When you see them, they are dependent, right? And well, A is very obvious. You can make the same claim, right? Yeah, and also, there are even more stuff that you can discover. For example, in here you may find that after all, B is not independent of D is not independent of B given C. It's a kind of a strange independence property that is not honored in here either, right? So you can try. I'm not going to enumerate all that. There are no DAGs, okay, which encodes exactly the same set of conditional independencies in this set. Okay, meaning that not every distribution has a perfect map, in DAG. But I can actually find a graph which encodes this distribution, which is this. Okay, we're going to now run into a new type of graphic model where your directionality in the edges are dropped, and you can actually show to yourself after this lecture that in this graph there are no more conditional independencies but only these two. And you kind of get the sense already, right? So A and C are graphically separated by D and B. And A and C and B and D are graphically separated by A and C. This is a new type of separation that is not called D-separation. Okay, it is a separation, graph separation in undirected graph, and they actually correspond to the set of independencies in this type of graphic models. So without further ado, I'm going to now use this as a kind of a example to motivate, in fact, this undirected graphic model paradigm. It's needed because it allows you to be more expressive and more precise about a certain type of conditional independence distributions, and also it captures a lot of natural phenomena. So here is a high-level description. In the undirected graphic model, locally, they only describe you pairwise relationship, no causality. Okay, it's not like someone is a parent of another one and so forth. And also you can write down the model, and you can also even put scores on some configurations. Okay, for example, certain pair of nodes are more likely to take a value or getting more rewards in taking certain value, and otherwise, if for other configurations, you can still do that, like what you do in probability, but you cannot use this to generate examples, like what we do in the Bayesian network. That given parents, I simulate a child or children's using conditional distributions. You have no mechanism like that. So there is no this causal or generating semantics. And also the constraints, can be also introduced, to impose contingencies and so forth in the graph in a more symmetric way. Okay, maybe I should use a few more examples to better inspire it. One of my favorite example, I presented in many places. You probably know that already, but I'm going to show it again for those who haven't seen it. There are many problems, in computer vision, which amounts to labeling the pixels. Okay, labeling the pixels. So now I have a graph here. It's a patch inside a bigger graph, and there are pixels. Okay, and I want you to label. I already gave you the space of the label, which is air or water. How do you label this? Now, I gave you just this. You label it. Do you have a way to label? How about water? Please raise your hand. Mysteriously, we have few people believing in water. How about sky? Okay, now roughly the same. A majority don't have an opinion. Fair enough. At least I see randomness, right, in this label. There isn't a unilateral or kind of a very aligned opinion about that. Now, I will make the problem simple by showing you this. Okay, so now, what do you label? Water, right? Well, it is actually on the top of the picture, which still could make it a sky, right? But somehow you see beaches and writing here. And then there is this continuum, basically going off the beach all the way to the right? And is that the way you draw conclusion, or you have other tricky mechanisms? Yeah, behind your conclusion, there must be a mechanism, an algorithm, right? And if you use the algorithm I just used, based on transmission or continuity of labels, it deserves a model to describe that, right? Any assumptions or any intuitions you have usually correspond to a mathematical model, okay, if it is explicit enough and crisp enough. So this is a model that could carry your message. Basically, it divides the entire space, the image, into a grid. Okay, and then on every grid, I put a label. And then I don't call the grid, the nodes, independent. I make them dependent. And by kind of adding affinity of the nodes to its four neighbors, okay, east, west, and north and south. Okay, I could even add more. You can have northwest, east, west. You can have four other neighbors. That's fine. It's up to your choice. But this is probably the simplest way. And by that, I could, really even add one more contingency or maybe affinity on that, which says that if two nodes are next to each other and connected by an edge, I want them to be more likely to label the same. Okay, more likely, but not absolutely. They just have a more chance to be labeled the same. Okay, so that could also be mathematically expressed. Right? And what we did just now is actually, a way of, defining a model, which is actually known as a grid model, and in the most crude fashion. But it's also known as with some other fancy names I'm going to tell you. This model actually has been heavily used in image processing and also in lattice physics and any other domains. That really means that you have a probabilistic model where the random variables are symmetrically connected to each other, and you can put some contingency table to insert kind of preferences of patterns. Okay, if you go back to map to the Bayesian network world, you have something similar but not quite the same, right? Over there are causality and directionality. You can write down a conditional distribution of parents given, of children given parents. All this suggests the semantics to have a direction. Okay, but in here we say you can connect them symmetrically, and you can label, a preference of, a joint pattern and contingency over that. But there isn't who causes who and who is ahead of who and so forth. So that's a model that we're going to study. It's an instance of the undirected graph model we just see. And again, such models are also seen in other places. For example, in social media, in social networks. This is one of my favorite social network models coming from Bible. We're going to tell a few more stories after in the future about the nuance behind this model. But it is an indirect model, if you will. We just want to treat everybody equally, and here, of course, it appears to be non-equal because the size of the node is different. It's only reflecting the degree of the node. Okay, nothing more than that. But the edges are still undirected. And in biology, in natural world, same thing. You know, nature often uses this structure to organize not only physics and materials, atoms, but also organic molecules like proteins and other things. Right. So protein-protein interaction in biological literature are often treated as a unidirectional network. And of course, Go is by definition a grid. And if you want to model the energy of a particular gain configuration in favor or not in favor, you can also write a model for that. In the good old days, before AlphaGo, this was the canonical model for Go. After AlphaGo, there are some additional ingredients introduced to treat this not as a model only, but as a full image that you can actually define not only local patterns, but also global patterns and something like potential, something like trends, which is more globally interesting, than just the local configuration of how a pair of configurations are interacting. And there are also synthetic models for certain purposes. I don't know, some of you may be working on coming from LTI, for example, or robotics. And sometimes you may be interested in multimedia data modeling, multi-view models, for example. Say you want to model a particular individual and using pictures and also their social media contents like text. But it's coming from the same person, maybe in fact with the same semantic underpinnings. Then you can introduce latent variables in here, and then connect them to observations in different spaces, okay, and produce a joint distribution so that we can model and do inference about the latent variables, sometimes known as topics. Topic model is actually an instance of such models. So we're going to see all these models down the road, in their specific context. But now let's return to the canonical definitions of what we have seen so far. So what we have just seen are instances of a big class of probabilistic graphic models known as the undirected graphic models. And in there, here are the key ingredients. First of all, you have an undirected graph H, okay, which gives you the topology I just mentioned. And then there should be something called a potential function associated with some kinetic components inside the graph. Okay. For example, what is a potential function? Let's say we have two random variables, x and x1 and x2. Okay, and in here we can basically put all their configurations. And if we were to write down a joint probability of these two nodes, we know how to do that, right? We're going to add some positive non-zero numbers between 0 and 1, and they should sum to 1, right? That's basically how we do probability. Potential function is something which often is known as pre-probabilistic, because I don't have to, in fact, follow any of the laws that I mentioned, to say numbers between 0 to 1 must be positive, must sum to 1, and so forth. I can well say, okay, 2 ones, I want to put a score of 10 there. Okay? And 1 and 0 and 0 and 1, I just like them to be 1, 1. And for both zero bottom states, I may want to put a 0 here. I can do that. Okay? In fact, if I do a twist in the future, I can even do more things like making them negative, but it's not possible here because after all, they need to be multiplied together and produce a joint probability. So they have to be positive.
Professor, is white like the same as like a type C, like a slide?
Yeah, you can call them psi C. Yes, in potential function YC. Yeah, thank you. Okay, you are with me, right? Because here I didn't take care of the normality, like they norm to 1 and so forth. Of course, when I multiply a couple of them together, I cannot guarantee that they still become a probability. Therefore, I need to have something called a partition function. That's a very, very important concept, in statistical physics and also in undirected graph models, which basically is literally just the sum of the product of all potentials and overall possible configurations. You basically put all these numbers together and across all the subsets that you define a potential and make sure that they come to 1 and you put as a divider here. Then you can always guarantee that the whole thing is norm to 1.
Yeah. An example you gave, you have to draw a slide. We have two sides.
No, it's one side is a table. Okay, function is a mapping of a configuration to number. So this side, I call them a potential function. So it is not a number. Okay, and in this particular case, this function is a table of this 4 number. In fact, I shouldn't put 0 here. I've been sloppy. I should put 0.1 here because if I have a 0, then it kills the whole thing. Everything becomes 0. Yeah, you don't have a 0 probability thing in here. Yeah?
You said the psi doesn't map to a number.
What's that?
You said psi doesn't map to a number.
Yeah, psi is mapping basically this guy's the configuration to a number. Oh, the question, he was asking what psi maps to. I actually answered, hopefully, the question, yeah.
So what is capital C?
Okay, good point. I'm going to get to that point. Capital C corresponds to the set of random variables of interest. You don't define such a number for everything, okay? Because if C is everything, you beat the very purpose of having a graphical model. You lose locality, and you actually cannot save any effort if you define the C for the entire set of random variables. Anyway, we're going to see it. So here, you only need to remember there's a potential function, there is a graph, and the potential functions are defined on subsets of nodes on the graph. And when you multiply them together, you get a distribution. This distribution, by the way, is called a Gibbs distribution. You already see something that's very interesting, right? So fields and Gibbs potentials, what do they remind you? Some college physics, right? Yeah. In fact, one of my first paper I read after I became a grad student was a Nobel Prize winning physics paper on statistical mechanics, which was talking about this stuff. Okay, all the literatures actually can be traced back to physicist literature back in the 30s and 40s. Atomic physicists, Gibbs, for example, is one of these great statistical physicists, even earlier than that. So if we have time, I can tell you a lot of stories about those, but now let's move on. All right, so you can see now that there are qualitative specifications in the form of the graph. We talked about that already. They correspond to independencies and that. But now comes to the quantitative part, which are the potentials. The potentials have to be, only needs to be, in fact, defined on a thing called cliques. Okay, so clique, as we know, graphically, you know what is a clique, right? It's the fully connected components inside a graph. And also, you can associate them with a little bit fancier concepts like a maxic clique, which means that it is the maximum subset of the graph that is completely connected. And if you include one more node, then it is becoming not completely connected and so forth. Just maybe use an example. So here I have a graph. What is the max clique? Right, I write the answers there already. Why the whole thing is not the max clique? Great, thank you. Right, and then of course I have subcliques. A pair of nodes is a subclique. A singleton is also a subclique, and so forth. So why clique is important? Well, remember, clique by definition means that they are totally connected. Therefore, there are absolutely no independencies or conditional independency within the clique. Every configuration is possible and has to be honored. If you have a bigger graph where things are somewhere disconnected, you imagine there may be some independencies. Therefore, certain configurations may not deserve any attention. Therefore, I don't need to write it. But when it comes down to clique, every configuration has to be associated with a characterization, such as a potential number or a probability mass. Right? So that's how potential is determined. I'm going to only define potential functions on the cliques. Okay, so that basically gives you where, you remember we talked about the YC. Why it's labeled as C? Well, C means clique. Okay, so that's basically the minimum unit where you have to define the clique or the potential functions. And what are these potential functions? Why they are called pre-probabilistic? Okay, so that gives you again a informal but still insightful justification. Just look at this graph. It has 3 nodes, and this is not a max clique, right? Because X and Z are not connected. Therefore, what is the max clique? Yes. Therefore, I have only 2 potentials. Basically. I could also have singletons. Okay. And but if we just follow the chain rule of probability joint distribution, here is a possible way that you can decompose them. You can decompose them another way. And then if you have to push them into the product of 2 terms, I bet you can arrive at maybe this multiplied by this, or this multiplied by that. That's probably the only 2 ways you can break the joint into a product of 2. And if you look at that, one is a marginal a joint distribution of 2 unknown variables. The other is a conditional of one node given others. There isn't a universal definition of these 2 things. Right. Therefore, if you just name a potential for either of them, they will carry different probabilistic meanings. Right. So a potential is not a marginal, not a joint. Unlike what we have in the Bayesian network, you always can call the building block, the minimum unit, to be a conditional distribution or a marginal of the root node. And then I also gave you examples before about how these potentials may look like. You can associate with actually a lot of interesting meanings. People sometimes encode compatibility there, and goodness of a configuration there, happiness, and so 2 people together may be very happy. Then you can also put a score there to award that kind of joint configurations. Yes.
Then what does a singleton function represent?
A singleton function, yeah, something have 1 node. Yes.
What is it compatible with?
Okay, very good question. Even without associating with anything else, I can still describe my state. For example, in atomic physics, you have upstream spin and down spin, right? And you can award the energy states, right? So that's actually a utility of such a singleton potential. You can also write pairwise potentials if they are repulsive, they are attractive. You can also describe them in the following way, right? Yep. Mm-hmm. Yeah. You can basically define either way you want. Yeah. Okay. Okay. Well, this is maybe a side note. I just say that it cannot be always, basically, if you have to attribute this to one definition of the meaning to have a probabilistic sense, I'm using a counterexample to say this is impossible, right? Because here, we know that according to Gibbs distribution, that this joint has to be expressed by a product of potentials, and I show you that these are the only 2 ways I can write down a product. And if you look at each of them, it is either a marginal or a conditional. They cannot be both conditional or both marginal.
Also, you're just giving a counterexample.
Yeah. Okay. It's nothing very profound. I'm trying to just convince you that forget about calling the potential function something probabilistic. It is not. Okay, that's the only message I want you to remember. So let's look at the clique a little bit more. So here we have this diamond graphical model, and we know that there are two max clique, and that's how you're going to use this to define the graphical models. I'm going to write down the clique potentials. In this case, the potential is a mapping of a triplet, right? A state of a triplet to some number, and you need to write a table for that. It's a two-dimensional table, right? It's a three-dimensional, by the way. Sorry, and then you can start using this to define a joint distribution. Okay, which is still better because if you don't use any graphical structure, you write this directly. You need to do what? A four-dimensional table with numbers in each entry. Now you need to have a three-dimensional table, which is still less expensive, right? And also it captures the conditional independence properties already, in this graph. Mm-hmm.
Like here you also say x1 with A, x2 with B, x3 with x4 with B.
You can, yeah. I've been sloppy here, yeah, but you can do the mapping by yourself. Okay, and what about the other cliques? In fact, every clique could have its intrinsic own potential functions, and sometimes people do that. Okay, I can use together, the triplet potential plus the pairwise potential, or I only use a pairwise potential. That's also fine. And then I have another way of writing down the joint distribution. Okay, these are called sometimes pairwise Markov networks, and that's a very typical and a particularly lazy way of writing graphic models. Yeah.
Pairwise things and three node cliques at the same time.
You can, yeah. In fact, that's what we call the canonical. The canonical basically asks you to have potentials for all the cliques in the graph. Yeah, sometimes overrepresentation is good. Because in fact, if you see neural network, it's a way overrepresentation, right? Having everything possible as a placeholder, and then when you train, you sometimes add, come up with a zero weights for that. So sometimes, in statistics or in applied machine learning, many people being lazy for a good reason. I just want to put enough placeholders to anticipate any outcome, but at the end, I know it is a sparse model because the data will drive the consequence, right? Okay, so I have a little questions here. Maybe you should do that as a homework. You can ask, here is a distribution called the P1. I only use the max clique. Here I have a P2, which I use the pairwise clique. And do I have the same set of independencies from these two distributions? And are the number of ways I specify the distributions in these two ways the same? Okay, I'm not going to answer that. You can go home and figure that out. Okay. And so to answer you, canonical representation really allows you to use all of that. Okay, and get a distribution. Okay, so go back to the graphical topology. This whole representation of undirected graphs is giving you a very, very simple kind of conditional independencies, using a simple graph property called graph separation. So now you're.
So you're splitting the potentials between three node map speed and also so x1 to 4 and x1 to have to be multiplied. We need a key for both x1 to 4 and x1 to.
You can, yeah, you still can. Yeah, basically now you are talking about three guys together, and when they form a certain configuration, I give them a score.
So isn't one
That could be. Yeah, that could be. Yeah, but they don't have to be. Right? You can imagine that, just imagine the human example, 3 people and 2 people behaving. The 2 people behavior may be different from the 2 people in the context of another guy. Right? Yeah, but you can choose not to do that, but that gives you flexibility. Yeah. Okay, so the I set of this graph is very simple graph separation, and that's basically a property known as the global Markov independencies. You can write, of course, a simple algorithm to collect all these independencies, which is known as the global Markov property. And there's another one that is also very interesting. That's practically useful in the future. I want you to remember that, which is known as the local Markov independencies. Remember, in the Bayesian network, if you still remember, I said that given any node in the in the Bayesian network, it is a conditional independent of the rest of the graph, given its parent, children, and children's co-parent. Right? Remember that law? It's a local property in Bayesian network. It's kind of awkward. Why children's co-parent matters? That's because of the V structure and so forth. Right? But in Markov network, it's a lot more intuitive. It's all your neighbors. Basically, it says that xi is going to be independent of like x minus I and minus something called a Markov blanket of xi. And the Markov blanket in this case is the direct graph neighbors of the node given the Markov blanket of I. Okay? So, yeah. Yeah, no difference. If you have an edge, if you have a thing in here, for example, then your Markov blanket are these 2 things. X minus I. Oh no, sorry. There should be a I here. It should be the entire X, the graph, right? It basically means the rest of the nodes in the graph except that node of interest plus its blanket. Now you see why it's called blanket. It kind of shields this thing away from that. So why it is important? You may wonder why we care about this or that. In fact, nowadays graphical models become unpopular because many of the techniques provided there are not popularly used because now we have a hammer, which is the deep learning that kind of goes everywhere. But certain properties still is useful. And I believe, of course, at some point when you find the limit of deep learning, you will still go back to use many of the other graphical model properties down the road. But here is one thing I do want you to remember even now. So this Markov blanket property is having the following usefulness. Even in deep learning, especially in deep generative models, it is a probabilistic model, and that generates samples and all that. And then you need to very often draw samples from that, conditionally on some evidence. Now, draw sample is a very difficult thing because you are going to be using a distribution of px given a lot of other things, usually p not x. God knows who they are. They can be anything else in the graphical model. Okay, and this is usually a gigantic conditional distribution because you are conditioning on so many things. Okay, in your universe, but if this universe can be modeled as a Markov network, then this one is equivalent to P of xi given MB of I. That's it. It is a much, much smaller conditional distribution because you are conditioning on a few things. So this equivalence is the core in the good old day Gibbs sampling algorithm, for example, which allows people to calculate atomic states. In fact, I believe the energy states to be determined when people design atomic bombs and stuff like that. or due to this kind of algorithm and tricks. You are having this piece of material, and you need to decide when is a stable energy, what temperature I need to reach to explode it, and so forth. Usually, they all use a statistical sampling algorithm, and one of the key trick used is this Markov blanket property, okay, to speed up the computation. So it's a speed issue. You actually get faster. All right, and again, we go back to the soundness and completeness. As usual, it's a leaky statement, but it's okay. It's almost tight, right? First of all, if P is a Gibbs over H, then we know that H is an IMAP. Okay, and then conversely, if your three sets are not following separation law inside H, then you will find them to be you will find them to be what's that? To be what I'm saying here. Yeah, you will find them in some of the distribution are factorized over H, which means that it's those are special distributions that you can design impedance, but not in all those. Okay, maybe the practical utility of that is to guarantee our very way of defining distributions to be the right way to do it. It's a very famous theorem called the Hammerschlag-Cliffords Theorem. It basically says that if you are using arbitrary potentials, okay, to formulate a distribution, and according to a graph such as AH, okay, then this particular form of the distribution is the only way to write proper distributions on that graph. That's the kind of guarantee that you can have. Okay. For any positive distribution over a V, and H is a Markov network given over V, then H is an IMAP for P. Then P is taking this form only. Okay. So that basically gives you, again, just like the factorization law, in Bayesian network, you here have something almost like a factorization. You can, discover all the cliques, okay, max cliques and the other cliques inside the graph, and write a potential function on top of that, and you multiply them together, you get a proper distribution on this graph, which automatically captures all the independencies, conditional independencies in the graph. Okay, so you don't have to do these numerous tests and examinations and qualifications of numbers just based on the set of conditional independence rules. All right. Now let's maybe revisit our bigger picture about perfect map, graphic models, undirected, and direct, and so forth. Right. So we know that there are certain independencies in a distribution for which you cannot find a perfect map in statistical in indirected graphic models. And in fact, likewise, you also there are certain conditional independencies that could exist in a distribution that you can never find or express them in an undirected graph. Okay, so basically, perfect map is not a entitlement, basically, for arbitrary graphs. Maybe just to make maybe the overall recognition more intuitive, we can use this Venn diagram to see how they divide the job and cover different type of distributions. So we know that there are something that the undirected graph model are very good at covering, but not by a Bayesian network. What is a typical structure that we see? You only see them in undirected graph, but not in directed graphic models. What's the topology? What? Can someone speak out? I feel like I hear a V structure. But somebody say something else? The diamond, right. So that guy, we actually used to open this class. In fact, is an example where you cannot find a directed graph to capture the same independencies, right? So it's actually the forte of undirected graph model. What about the directed ones? Are there something there that is not possibly captured in undirected graph models? V structure, right. So there's an awkward thing here which says that if you see something, then something gets coupled, right? And you don't see that kind of properties in undirected graph model. There isn't such a semantics there. And then what are they in the middle? Well, something like this. You can all basically encode the same independencies using directed or undirected, right? You may wonder what's there. Well, there's something else. There's something, but I don't think that's very interesting to discuss here. Okay, any other questions before I? Okay, there's another message I do want to pass before we run into examples. We said that in the specification of the potential functions just now, we are still forced to follow. Okay, so when we specify conditional dependence tables, there are a lot of constraints we have to follow, right? The number has to be between 0 and 1. It has to sum to 1 and so forth. And in specifying the potential functions in the Gibbs distribution, what are the constraints, if you remember? Yeah, of course, that's for sure. They have to be on some graph spectra. Yeah, I mean the number itself. I think someone there said something already. P positive, right? Because they need to multiply together. And in fact, it will be non-zero, right? Which is rather inconvenient. Sometimes people naturally react to something positively and negatively, right? And if you look at the physics literature, in fact, there is also a symmetry. For example, if I have a two-spin structure, and the spin, a upper direction and lower direction, why you call this 10 and call this 5? It's a little bit awkward, right? Why someone is lesser than the other one, right? And a physicist would call this positive 1 and this minus 1 because they are symmetric, right? So if that's the way you want to specify energy or potential, then the Gibbs distribution is inadequate, right? So here we have another way to do it. We want to introduce an exponentiated form of the potential function. Now it's known as the energy function, okay? And these are called exponentiated potential functions. And then your joint is now simply becoming, a exponentiated sum of the original potential functions, okay? And this guy, the sum of the whole thing was known as the free energy. And this distribution was known as the Boltzmann distribution in statistical physics. In statistics, it's also called the log linear models. And we're going to actually review why it's called log linear models later. Okay. So this is just for, as of now, convenience. You can now specify negative numbers to these kind of functions. And of course, domain specialists will have more interpretations. They will have more reason and motivations behind it, which we're not going to cover. Okay, let's see, what else? Some examples. So here is a Boltzmann machine. You have 4 nodes, and they are all pairwise connected. And then all you need to do is to provide a bunch of so-called pairwise potentials, and also singleton potentials. In fact, I should write the other set, which is Okay, and just for convenience, you can express this whole thing as a linear algebraic expression due to multiplication between vectors and matrix, right? So this maybe let's rewind. So there is also a more peculiar way of even writing down the potential functions. So we know one way already, right? Which is a tabular expression. Remember that? We basically put a table there and and put a pair xi and xj, and we see 0 and 1, 1, 0, and so forth, and I put a number there. That's one way. There is another way where the physicists are more maybe inclined to use, which is to directly, define the potentials as a function of as a simpler, linear function over the state value, because this x, their states can be numerical, right? They could be, if you call, for example, a upper spin and down spin, they are categorical things. You cannot multiply them. It's not a numerical number. But if you are willing to turn the state to be a number itself, say +1 and -1, or just some real numbers, then you actually have a way to use these numbers to define the potential functions more directly. And here is one way. We basically just define the pairwise potential to be the product of the two states multiplied by a weight, theta. And define the singleton potentials to be the numerical value of that state multiplied by another weight, alpha. And that actually allows you to express the whole energy function a lot more tightly as a linear algebraic product. Here, this huge matrix theta is actually like this. So how does theta look like? It actually is this. In the middle, you have a alpha 1, alpha 2, all the way down to alpha n, assuming n random variables. And here you have theta 1, 2, theta 1, 3, and theta 2, 1, and so forth. Okay, so you basically just systematically organize all these weights into a matrix, and then you multiply them, with left multiply and right multiply them by the states, subject to a offset, which is having some. It's a constant basically that you can always take it out or put it there just for mathematical cleanness, and that gives you basically a quadratic form of the energy function. Yeah.
So the constant c in the first experiment, just there to facilitate the quadratic form.
Yeah, the constant c is something that you need to use to make the whole thing a constant, a normalized distribution. Yeah, yeah.
In that matrix, alpha will be coefficients of squared x's, right?
Yeah. Thank you. Actually, is it? Not necessarily. Let me see. Yes. Mm-hmm. Okay. That's not right.
Already incorporated in the term before, because I and J.
Yeah, right. Yeah. Anyway, I think it depends on how I manipulate the indexing to make them crossing each other or to be next to each other. But the point is that you can define the singletons any way you want. A quadratic, a linear, or a cubic. That's all possible. And one of them can allow you an expression like this. Okay. Clear? In fact, you will see a lot of interesting things in here in the Bose machine where people use this trick to either both allow convenience in calculation and expression, and also in richness in capturing various atomic states that people care about. So this model, in fact, has a name. It's called the Ising model. Okay, it has quadratic states and singleton states. Okay, And it was originally coming from the atomic physics, but later on it was used in image, in fact, a lot. Yeah.
Quick question on the previous slide.
Mm-hmm.
For the capital theta matrix, does that have to be like positive semi-definite?
Yeah, you have a lot of properties in there.
I mean,
It depends on the way you define the potential functions. If usually in this case, it is a positive semi-definite matrix.
so I mean, correct me if I'm wrong, but if that's positive semi-definite, then we could look at the h on the bottom as like the magnitude of vector out b multiplied by the square root of it.
Yeah. In fact, if you play with this a little bit, if the pair is not discrete but continuous, this actually gives you a Gaussian distribution. You actually can have that. We are going to, in fact, study that later. There are a lot of special cases leads to a model that you are familiar with. But yeah, all we want to say is that there can be certain properties in theta that makes the distribution following special properties. Okay, but in the, well, I think, yeah, it is. But you can actually define other distributions, Can I? If I have a, yeah, I think in the Undirected model case, the H has to be positive definite. Yeah. Okay. Easing model. Oh yeah, so you may want to hear another model called Potts model, where the states, number of states for every node is not binary. They can be multi-states. These are again coming out of the physics world, where a atom or a molecule are not a binary state. But in image, if you use RGB color, already you have 3 colors, in a particular pixel. Then that's again using a Potts model, right? So they have an interesting physics root, where the first inference algorithm, learning algorithm, actually were reported in those literatures. I just want to flash at you a few other examples, just for fun, and so that this model has been quite popularly used as it is, or as building blocks of some other models. So, for example, this is a model that is actually very important for the literature of machine learning and deep learning. It's called the restricted Boltzmann machine. Okay, so graphically it is like this. You have 2 layers. One is hidden, one is visible, and they are connected in a bipartite fashion like this. And defining a joint can be done in multiple ways, and here is an easy way. You just literally write down singleton, and pairwise potentials in a certain way. So you have a globalist definition. Okay, so why this model is interesting? I'm going to tell you a number of stories down the road about its deep connection to the deep neural network that we are now enjoying and playing so popularly. Okay, for example, if you add another thing on top of it, you can keep adding that and makes a deep neural network. Okay, and also when you do inference in this 2-layer model only, the computational graph that you follow to track each step of your inference is also very, very related to what we now do as a backpropagation inside a deep neural network. There are computational connectedness and the model connectedness. But this model was originally put forward by, well, I should say, reverberated by Hinton in some of his applications, and then becomes one of the foundations of later fancy graphical models. I personally also played with this model a bit and wrote some papers early on. And there are some interesting ways of using it that can be very, very useful. Maybe let me mention a few words about that. First of all, this graphical model, why, for example, you ask, why not we do a directed graphical model, which also gives you a bipartite graph, but have a direction. Hidden points to observed. Isn't that obvious, right? People actually do that very often. But why the RBM becomes particularly interesting? That's because of a computational reason. Again, the the different mission between if there is anything, or maybe the only thing that differs machine learning scientists from statistician, why we are in computer science department and why they are in the STAR department or in a liberal art department, is because after putting forward the model, we need to solve it, we need to compute it. Therefore, your computational algorithm in doing the inference learning becomes as important, if not more important, than the model itself. Right? We're not talking about the hypothetical things. And here, when you put an edge here, or when you're not putting an edge here, or a direction here, or not putting a direction here, make a huge difference in computation. That's the only, maybe one of the most important distinction. Can somebody tell me why, if I have a direction here, I'm going to run into trouble in computation? Yes, there are a lot of V structures. Look at this, right? So here I can actually have a V structure of a huge bundle of nodes. Let's imagine here I have 100 hidden nodes. Then these 100 nodes, given the observation, suddenly become coupled. Therefore, when you do sampling or conditional distribution of any of one, you have to also look at the other 99, right? But in this case, your conditional of the hidden, okay, given the observation, can be perfectly factorized by a product of every individual hidden node given whatever observations. And that makes the whole thing a lot easier. Okay, so yeah, in terms of richness of expression of independencies, you lose some, but in computation, you lose a huge. That's why this very algorithm known as a inverse skip sampling was possible, because you can just iteratively sample every single node independently and get to convergence. Okay, so that's a thing we're going to strike on and on in the future, where modeling mathematics is tightly coupled with computability and the efficiency of algorithms. And also there are, with the graphical model, undirected graphical model semantics, you have a number of interesting ways of defining the distribution in a constructive fashion. You don't have to write down in this way, which force you to write down these kind of potential functions, sometimes in a less meaningful way. So what do you mean by a potential function of a single node? Or a potential function of a word? I don't know what that means. Or a potential function of a topic in here? I don't know. But if you are able to factorize it and make them into a component in the form of this, okay, which is allowed in a Markov random field, you actually could attribute specific meanings. So this was a model I did many, many years ago for text modeling. It's at that time positioned to be the equivalent of what is now known as the topic model in the undirected space, where you have topics and the words, but they are not directional. And the way to define this joint is very easy. I didn't even go to the joint. I just specify each local conditional in its natural way. So here are the topic given the words. And you can use a normal distribution, because topic is maybe a intensity type of concept in a particular semantic space. You can say that when I see a lot of White House, this is more likely to be a political topic. Then I can have a Gaussian distribution to really capture my uncertainty and concentration of the belief, right? And then here, this is the probability of the word given the topic. If you see the topic to be politics, what's the probability of seeing a word, say White House or Congress and so forth? You can also write down as a binomial probability of word frequencies or word strengths. Right? So these are the local list definition that is sometimes very interesting. And easy and intuitive to specify. Sometimes more easy than writing down this joint conditionally together. Right? And in fact, if you work out the mathematics, they will give you a very consistent global distribution after combining the two conditionals in a specific way. Okay, I don't have much time left. I will just flash at you some names of other important models which we are going to in the future use as reference points and also running examples for other problems. So there is a model known as the conditional random fields, which was also invented in CMU by Professor John Lafferty, again, maybe 15 or 20 years ago. That was a very famous paper. That was also one of the first paper I read as a grad student. It was so difficult. The whole reading group in the team spent a week just reading the single paper. Now you can see it's very simple, but at that time it was revolutionary. It is a model that is following a graph and capture a problem that we know already. So what is this model? It's a Markov, hidden Markov model, right? And it was used to model sequential events, right? So there is a counterpart of this model in the undirected world where all the directions are dropped. Okay, so this is a conditional random field. We're going to study why it is interesting in the future, but at least semantically or syntactically, you know that it is a model that can be defined in this way. You just write down a huge conditional distribution of all the hidden random variable given the observations using a collection of these potential functions. Okay, these potential functions can have very interesting interpretations. Did I give you anything? Yeah, I have something. Yeah. So, for example, I can use something called edge potential to describe tendencies of seeing a pair of words, a pair of characters, and so forth, so that they demonstrate. For example, if you want to do spelling checking, in your keyboard, if you see N and G together, I think that's probably a very high likely pair to happen, right? But if you see a N and a Z together, chances for the word to be misspelled is bigger, right? So that's the kind of thing that you can capture, in this kind of a conditional random field. And also you can have other singleton, potentials which captured the probability or the tendency of a particular event, say a character appear or not. And also the potential functions can be even more flexible than a conditional in capturing some global effects. Are these particular word bold-faced? Is there a bracket next to it? Or are they in the same line inside a text? All these actually can be incorporated into the design of these potential functions. That's why actually conditional random field is a great template for feature engineering and has a lot of utilities in natural language processing. And we're going to work out how to compute this model in our later lectures. And also remember the CRF is not just a sequence model. It could be also a more higher dimensional model. For example, for an entire plane, you can also define a CRF to capture that kind of property we just mentioned, that the pixels next to each other are likely to be aligned and so forth. And I think that's it. At the end of the day, the gist of today's lecture boils down to a graphical model that has this type of conditional independence properties, which is known as the graph neighbors as the Markov blanket. And let's see. And I want you to really at least remember these three very popular undirected graph models. We have actually one more note. I wanted to say a few words, but we ran out of time, which is an algorithm that helps you to discover the structure. Okay, I have 2 minutes. Let me just say a word that gets you hopefully. Oh, I don't have the material to say that. Actually, did you ever worry about where does this graph structure come from? Do I just draw it arbitrarily, or you can also do a data-driven approach? I will set up the question for you, and then we're going to revisit it at some point. In fact, the graph structure itself can be learned also from data. That actually makes many people feel that we can really push forward data-driven causality inference. Okay, I can do interpretable machine learning, interpretable AI, which is a very glory word these days. Everybody's talking about that. I will have some good news for you. I will have some bad news for you as well. Okay, the bad news is that The good news is that such algorithm exists, that you can uniquely discover a structure which is probably correct, but under certain condition. Okay. And also the bad news is that for most of the conditions, you cannot uniquely discover a structure. There are many structures giving you the same score that you like to optimize, such as likelihood. And therefore, the so-called causality is a total statistical effect, not necessarily a natural cause. And we're going to actually discuss that in our future lectures.